Okay, so if you have the natural log of A minus the natural log of B, that's the natural log of A over B. So that means we can rewrite what we just had as the natural log of Q minus the EMF times C over negative EMF times C. That's just that those two log terms equals minus time over RC. Okay, now remember what we're trying to do. I think we're trying to find Q, right? We're trying to find Q as a function of time. So if we want to get Q out of that natural log, you exponentiate both sides of the equation. So you basically say e to all this and e to all that, okay? Because e to the natural log of something is just the thing. So Q minus the EMF times C over minus the EMF times C is e to the minus t over RC. Okay, and then we can bring this up here, and then you'll have Q minus EMF over C and bring that to the other side, and then you'll end up with Q equals the EMF times C minus the EMF times C times e to the minus t over RC. So I just brought that over there and then brought that over there to get Q by itself. We're getting there. Now let's say Q equals the EMF times C times the parentheses 1 minus e to the minus t over RC. And this is probably where we want to stop and think about what's going on. We've done a lot of algebra. So our differential equation told us that this thing is a function of time. To solve it, we had to integrate. A little trick in there. We integrated, we solved, we did algebra, and eventually we got, here it is, as we said, the charge on the capacitor plates is a function of time. And if we look at it, it actually makes a lot of sense. Let's see, what is special about EMF times C? Well, if we were to ignore the resistor and really not really think about current flow, what would happen if we just had a capacitor here and a battery here? Well, this would be at a high potential of the EMF, and this would be at a low potential of the difference of the EMF. You'd basically just be putting a potential difference of the EMF over the capacitor. And these would just be wires, right? There's no resistance, there's no real current flow to worry about. And then you would have just the definition of capacitance. You would have that the charge on the wires would just be the EMF times the capacitance. So it does kind of make sense that this is what should be here, because if you look at the function, this is the maximum value. Sometimes you call this Q max. The maximum charge you're going to get on this capacitor is the EMF times the capacitance. It makes more sense actually if we plot it. Let's go ahead and plot now. Didn't leave a lot of room, but let's plot versus time Q, the charge on the capacitor. Okay, at time equals 0, early time, that's when we first threw the switch. Let's see mathematically what it tells us. E to the 0 is 1. Doesn't matter what all this is. If we have e to the 0, that's 1. 1 minus 1 is 0. Doesn't matter what Q max is. Q is supposed to be 0 at t equals 0. It had better be, because that's what we put in our integral limits, right? So when we flip the switch, we said it was 0, so sure enough, you get 0. If we wait a really long time, let t be really big, let it be infinity, right? E to the minus something is 1 over e to the something. E to the infinity is big, 1 over e to the infinity is 0. So basically, this is an exponential function that goes to 0 at really large time, t. So if this goes to 0, this is 1, then sure enough, at long time, this goes to what we call Q max, the maximum charge of the capacitor. So we could put a line here and say this is the EMF times the capacitance. This is the maximum value this function goes to. And then you just have to know about exponential functions and know what this is going to look like. It's going to make its way from 0 to the maximum value, kind of like that. Not the best one I've ever drawn, but that's the idea, is it makes its way up towards the maximum value. So this is how you can track the charge in this case, and it matches pretty much what you would expect. You close the switch, current flows, the current is affected by the size of the resistance, but it slowly builds up charge onto the plates, and eventually you reach a steady state value of EMF times C.